Hey guys, so last time we talked about things like alphabets, strings, languages, regular languages, finite state automata, and the big idea of the last video was that we showed that English is not a regular language. So this video is going to be dedicated to exploring what English is and what we can use to model it. If you haven't seen the last video, be sure to check it out before watching this video, and I hope you enjoy. Alright, so far we've been talking about automata, and just to review for a second what automata were, basically the fundamental idea about the automaton was that you feed in a string and it tells you whether or not the string is in our language. So in other words, it solves the decision problem for our language. Now we're going to switch gears a little bit. We're going to talk about a different perspective called generative grammars. And basically we're just going to call those grammars from now on for short. Okay, so the idea is that instead of feeding a string into the automaton and it telling you whether or not it's in our language, the generative grammar is going to tell us what all the strings in our language are at once. So that's the idea about what we want to accomplish with this generative grammar. So let's just get right into it and talk about a few of the components of a generative grammar. So basically the generative grammar runs on these things called rewrite rules. And if you ever used a word processor, you know exactly what a rewrite rule is. It's just find and replace. So let's give it a brief example. So rewrite rules. And again, my handwriting here is not that great. But let's say you have the string cat. And we're going to say we have the rewrite rule, A turns into O. Okay? Now, if you apply this rewrite rule to the string cat, what do you get? You just get the string caught. So that's the basic idea behind the rewrite rule. It looks for the thing on the left and then turns it into the thing on the right. And that's what we're going to use to create our model of generative grammars. So let's just give one example of a generative grammar. So we're going to solve the problem for the language that we came up with earlier that we used in the last video. So we want to find out all sequences of nickels and dimes that add up to 15 cents. Okay, and so I'm going to create a sample generative grammar for this. Certainly there are multiple possible grammars you could write, just like how you can write multiple possible automata for a single situation. But here is what I'm going to do. And just notice I've written A in two different ways, so just ignore that. But the fundamental idea is that, let's see, we're going to start with 15 cents. Remember, this is exactly what we did with the automaton. So I had the automaton right here. Let me just pull it up. So right here, we started with the 15 cents in the start state, and we counted down to 0, right? And we're going to do the exact same thing in the generative grammar. So we're going to think about it this way. 15, you can break up into 5 and 10, right? So you can break up 15 into a nickel and 10. And likewise, you can break up 10 into 5 and 5, right? So you can break up 10 into a nickel and 5. And lastly, you can break up 5 into 5 and 0. So this is that what we're going to do, a nickel and 0. And 0 we don't really care about, so we're going to rewrite it to the empty string, and that's just going to get rid of it. And we can do the same sort of process with dimes. So if you have 15, that's the same thing as 10 and 5. So in other words, it's a dime plus 15. Or sorry, a dime plus 5. And now 10 is a dime plus 0. Okay. And these are going to be all of the rewrite rules of our grammar. So what is a grammar? It's just the combination of a start state and the rewrite rules that we can apply to it. So let's just give an example of how to use this generative grammar. So recall that, we figured out that 3 nickels add up to 15. So in other words, n is in our language. Let's try to see how we can generate n using this grammar. So I'll just write an example here. So if we start with 15, well, our rules say that we can replace 15 with n10. So let's go ahead and do that. We're going to replace 15 with n and 10. So far, so good. Now we can replace the 10 using this rule with n5, right? So the 10 is going to turn into n5. And I'm going to carry down this n here. Awesome. And now this 5 we can replace with n0. So let me go ahead and do that. This 5 turns into n0. And lastly, the 0 can go right away, right? Because the 0 turns into an empty string. So we can just get rid of that. And so you can see that we've generated the string n. And that's why it's called a generative grammar, because it gives you rules in order to generate the strings that are in your language. Okay. And so there are two different types of symbols in these rules here. There's the symbols that are part of our alphabet, so the N and the D. Those show up at the end of our derivation, so we're going to call it a terminal symbol. So terminal symbols are going to be the members of our alphabet. So in this case, it's just N and D. And what about these intermediate symbols that we sort of get rid of in the process of generating the string? Well, we're going to be a little bit uncreative, and we're going to call them non-terminal symbols. So these we're going to call non-terminal symbols. Non-terminal symbols. And so the examples of those would just be the 15, the 10, the 5, and the 0, right? And you might notice, well, there are some direct parallels between this way of thinking about it, about the grammar of the language, and about the finite state automaton of the language. And it turns out these two approaches are exactly equivalent. So you'll notice here the terminal symbols are exactly like the alphabet that we use for the finite state automaton, and then the non-terminal symbols are exactly like the states of the automaton. So our states were named 15, 10, 5, 0. Those are exactly the non-terminal symbols we have. And then these rules here are basically the transitions between the states. So remember we had, 15 goes to n, 10. That's exactly what we have in the finite state automaton. 15 goes to n and 10. And so you might ask, for every finite state automaton, can you make a grammar for it? And the answer is yes. So for any finite state automaton you can have, there is sort of a process that allows you to convert it to a grammar. Okay. So we can make a sort of formal definition for the generative grammar. This is completely mathematically rigorous. You can define like the set of symbols, the alphabet, the rewrite rules, the start symbol, etc. But the details here really, again, don't matter too much. So what matters really here is the idea of what we're doing. Okay, so recall that we defined regular languages as any language you can make a regular, a finite state automaton for. Can you do the same thing with grammars? The answer is yes. So if you limit the grammar rules to these three forms of rules here, it's a little bit arbitrary, but these three types of rules, it turns out that the languages you can generate using these types of grammars are exactly the same as the languages you can generate with a finite state automaton. So in other words, there's an equivalence between these regular grammars and these finite state automata. So again, the regular grammar is the ones that have rules of the type A goes to empty string, A goes to little a goes to little a, b, things like that. So just to give an example of what wouldn't be allowed, you couldn't have, say, 15 going to 10 and 5. And the reason this isn't allowed is because you can't have two non-terminal symbols on the right side of the regular grammar. You can only have one, and that's represented by this b here. Okay. And it turns out that, anytime you have a regular grammar, you can make that into a finite state automaton, and anytime you have a finite state automaton, you can make that into regular grammar. And the process is honestly very straightforward. So I'll let you guys hammer out the details. You can post in the comments if you figure out exactly how the process works to convert a regular grammar into a finite state automaton, and vice versa. But I'll just tell you right now, it's pretty straightforward. The details aren't really important for now. What matters really is that, what happens if we remove these restrictions and we allow for a more diverse set of rules? So for example, what if we do allow for the 15 goes to 10, 5 rule to be in our grammar? What happens? Well, it turns out that if we allow these types of rules, we can generate a larger set of languages, right? So, if we upgrade the amount of grammars that we consider, then those grammars will generate more languages than we previously had access to. So there are trade-offs here where we can figure out a larger class of languages. We can consider a larger class of languages. We can model a larger class of languages. But the important thing here is that the complexity of our system goes up. So when we had this regular grammar, we had really simple rules. It was really easy to figure out the behavior of any sort of string in the language. And remember, we had an O of n processing time for all the strings, where the n is the length of the string. And this dramatically changes when you consider rules of this form. And we're going to call these context-free grammars. Okay, so if you think about solving the decision problem for a context-free language, what happens is that the processing time shoots up from O of n to O of n cubed, and it turns out to be a really big difference in the complexity of the language. So by removing restrictions in the type of rules that we can consider in the grammar, we've expanded the classes of languages that we can model using this grammar, but we've also increased the complexity of the language. So there's a trade-off here. So in the regular grammars, we had rewrite rules of these three forms. For the context-free grammars, we scrap that and we can say the rewrite rule will be of the form A goes to any string. So we can consider 15 goes to 10 and 5, 15 goes to 5, 5, 5, 15 goes to n, 5, n, 0. All of these are now valid rewrite rules in our language. And that allows us to model a much larger class of languages. And we're going to call these languages the context-free languages. So any language that we can write a context-free grammar for, we're going to call it a context-free language. And so the word context-free, that name might not seem really obvious to you right now, like why is it called a context-free language? But it's going to become clear towards the end of the presentation, and we'll contrast it with a set of languages called context-dependent languages. But we won't get into that right now, so for now just accept that it's called a context-free grammar, a context-free language. We'll explain why later. Okay, and it turns out that these context-free grammars give us access to a really important tool called a parse tree. So you'll notice with the derivation we did earlier, it already sort of looks like a tree. So let me just redraw it here. We had 15, and then the 15 splits up into an n and a 10, and then the 10 splits up into an n and a 5, and it splits up to an n and a 0, and the 0 turns into an empty string. And the way we read that is the final string is just these bottom nodes. So the final string is n, 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 and then we ignore the empty string. Okay, and that's called the yield of the tree. But basically the idea here is that when we have a regular grammar, you can see the tree is really limited in the way it can grow. So you'll notice it only grows to the right, and it really grows into the right in a really restricted way. So that's how we know that it's generated by regular grammar. But it turns out with the context-free grammar, we can do more things. So we could have, for example, a tree that looks something like this, where it branches in both directions. We could have a tree. So you can see it branches both in the left and the right, and the number of nodes that we can consider dramatically increases, and so the complexity of the structures that we can model increases as well. Okay, so the basic idea here is that, let's say, remember that the language a to the n, b to the n, where n is some number, some integer greater than or equal to 0. So remember we proved last time this is not a regular language, but it turns out this is actually a context-free language, which means we can write a context-free grammar for it. So let me just tell you right now what that context-free grammar might look like. So our start state, I'll just call that S for start. And then we're going to have two simple rules. So the first rule is that s can turn into s again, but with an a to the left of it and a b to the right of it. And the second rule is that s turns into the empty string. So s can disappear from our final calculation. So let's take a look at how we might generate the string a, b, 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 using this context-free grammar. So this stuff I put in the box here is the grammar we're looking at. Okay, well, it's actually fairly straightforward to generate the string. So we start with s, and then we apply the first rule. So we apply that the s turns into a, s, b, and we apply that rule again. So we get another a, s, b. So a, s, b, and we apply the rule one more time. And you can see that we're really close because we have 3 s's on the left and 3 b's on the right. And now all we have to do is get rid of this s here. So s turns into the empty string, applying our second rule. And now you can see we've generated the string a, b, b, b. And so you can see sort of the power of these context-free grammars. You know, with the finite state automaton, we had no ability to model this language, a to the n, b to the n. But now, with the context-free grammars, we can model these languages. Okay, so I'm just going to go over a couple properties of the parse trees here. So 2 important properties here are the height and the branching factor. And those are really easy to determine by this picture. So I'll show you right now. The height is just, you know, how tall this tree is. Right, so if we start here, we can go down 1, 2, 3, 4 steps. And so we say that the height is 4. Okay, really simple. And the branching factor is also really simple. It's just how many lines can come from a single node. Okay, so for example, with this start node here, there are 3 lines coming out of it, right? 3 branches. And that's the maximum that a single node can have coming out of it in this tree. So you'll notice every node in here either has 3 lines coming out of it, or 1 line coming out of it, or no lines coming out of it. And so we say the maximum is 3. So the branching factor here is 3. Okay, and so why do we care about these properties? Well, the important result that we have is that the size of the string we can generate is limited by the branching factor and the height. In fact, it's exactly equal to, so the length of any string generated here is less than or equal to b to the h. And so you might ask, like, why this is. Where does this formula come from? And I'll give you a little bit of intuition from it. You can actually prove it pretty simply using straightforward induction. So that's like a nice exercise if you just learned how proof by induction works. But you know, I'm just going to give you some intuition here, so I won't get into the nitty-gritty of it. But basically, let's say you have a tree with branching factor 2 and height 4. So we start with a single node at the top, right? And then that can branch out a maximum of 2 times. So let's say it branches out twice, right? And now each of these nodes can branch out twice. So it can look something like this. And so you'll notice that the number of nodes we have at each level doubles. So let's do it again. Now we have 8 nodes at this level. So it went 1, 2, 4, 8. So in other words, the number of nodes that we have can grow exponentially. And it's all based on this branching factor here. So since the branching factor is 2, we multiply by 2 each time to get the new number of, the maximum number of nodes. All right, and you can see that, if we draw all the nodes down here, I would draw a total of 16 nodes, and that's the maximum we could have in a tree of height 4. So in other words, the length of the string we can generate, which again is just the number of bottom nodes we have, the length of the string is limited by 2 to the 4, or 16. Okay, so that's some intuition behind this formula. Why is the length of the string less than or equal to b to the h? It's because at each level, the number of nodes you have in the tree grows exponentially. So if b is 2, it can double. If b is 3, it can triple. If b is 4, it can quadruple, right? And h tells you how many levels you can have at max. So in this tree, we have 4 levels. So starting from here, we count 1 level, 2 levels, 3 levels, 4 levels. And so the maximum number of nodes we can have on the tree, on the bottom of the tree, is 2 to the 4, or 16. Okay. And it turns out this fact is going to be really useful. This is going to be the main idea of something we're going to prove next. So the basic idea is that, you know how we proved the pumping lemma for regular languages, and we used that to figure out how many, we used that to prove if a language was not regular. Well, it turns out we can do the same thing with context-free languages. So there exists a pumping lemma for context-free languages, which we can use to show that a language is not context-free. Okay? And so remember, with the main idea with the pumping lemma, the original pumping lemma, was that we wanted to show there's some sort of loop that we can traverse an infinite number of times. And this is exactly the same main idea for the pumping lemma for context-free languages. So let's have n be the number of rewrite rules. So n is the number of rewrite rules, and then let's say we have some string this is the parse tree for some string that's generated by our language. You know, maybe the tree looks something like this, and then we go down a number of steps, and then we go down here, and then there's more. Right? The tree might look something like this. I don't know. It's just a random tree I drew. But the main idea here is that, you know, for each of these lines, we're applying some sort of rule. So this is one rule. This line is one rule. You know, all of these guys here are rules, and then this line is a rule, etc. So this line is a rule. And so let's have a tree with height greater than the number of rules. So let's consider a tree, and the height is greater than the number of rules. Well, that means we used one rule at least more than once. So in other words, there's some sort of loop. We can keep applying that rule. So the original pumping lemma, it was that we used, you know, some of these, we went to one state more than once, and now we're applying a similar strategy with, you know, using one rule more than once and showing that there's some sort of loop that follows if you apply a rule more than once. Okay, so the idea here is that one rule must be used more than once. And so because of that, there has to be some sort of loop. And so now you might say, well, how do we know that the height of our tree is greater than n? Well, remember that the amount of the length of the string we produce is limited by beta to the h, right? So let's say we have a string which is greater in length than b to the n. Well, that means the height of our tree must be also greater than n, and so we must have applied a rule more than once, and we have some sort of loop. And that's the idea we're going to use in our little proof here. And so that loop can be traversed as many times as we want. So in other words, we can pump the string that's the part of the string that's generated by loop, and we get new strings that are also part of the language. So this is, you know, probably the hardest part technically of this presentation, but it's exactly the same as the original pumping lemma that we proved in part 1. Okay. So this is the formal statement of the pumping lemma for context-free languages. It's not really too important, but I wanted to include it because I just want you to see how similar it is to the pumping lemma for regular languages. So the parts in red here are the parts that I changed from the original pumping lemma. But everything in blue here is exactly the same. So if I just flip back a bunch of slides right here, you know, we can see it almost looks exactly the same as the slide I just showed you, except the parts in red are different. So I changed regular language to context-free language, and now we're pumping 2 different parts of the string instead of one part of the string. And that's just because this system for generating strings is a little bit more complicated than the system for generating strings we were considering before. So we have to pump, you know, 2 parts of it simultaneously instead of one. But there's really, you know, no fundamental difference between this pumping lemma and the one before it. So it's the same exact sort of logic. It's just the machinery is a little bit more complicated. Okay, so can we do some sort of example of this pumping lemma for context-free languages. So we have this language, let's say a to the m, b to the n, c to the m, d to the n, and we can use the pumping lemma for context-free languages to prove that this is not context-free. So in fact, there are languages that are not context-free that you cannot write a context-free grammar for. And the way we do this is that it's the exact same as the way we prove that a to the n, b to the n is not regular. Right? We just use the pumping lemma and we do some sort of a proof contradiction to show that this language cannot possibly be context-free. Okay, so I'm not gonna go through all the details here of the proof. It's pretty messy. There's a lot of cases you have to consider, but it's exactly the same idea as the proof that a to the n, b to the n is not regular. So you apply the pumping lemma. So first you assume that L is context-free, and then you apply the pumping lemma and you show that some sort of contradiction follows from that. And then from that, you can figure out that L is in fact not context-free. Okay, and it turns out the reason that is not context-free is because it has these things called cross-serial dependencies. So informally, this is basically when we have the a to the m, so the number of a's is the same as the number of c's. So the a's and the c's share dependency, and I drew that with a little line here. And then the number of b's and the number of d's is also the same. So there's some sort of dependency between the number of b's and the number of d's, and I drew that line here. And basically when these lines cross, it's called a cross-serial dependency. And if you can have arbitrarily high number of these crossing dependencies, then that's something that cannot be captured using a context-free grammar. So now the next logical question is, are all natural language context-free? And the answer is no. One common example that's cited is Swiss German, and basically the idea is that these lines cross each other. So I have one part of a sentence here. It's that we let the children help Hans paint the house, and then if we translate that to Swiss German, the word order is a little bit different, and you can see that the children aligns with let, and then Hans is connected to help, and then house is connected to paint. And you can see that if you just plot out all the lines that connect these words, they all intersect, and you can make an arbitrarily large number of these intersecting lines in Swiss German. And so that's one reason why Swiss German is not context-free. And so you might ask, is this true of all natural languages? For example, is English context-free? How could we figure that out? Does English have these sort of cross-serial dependencies? And so, the answer is that, it's currently not known whether English is explicitly not context-free. But we do think that context-free grammars are not a good way to model English. So to give an example, let's take this sentence. He didn't give the presents to Mary, but I think Bill did. So in this sentence, there's no explicit cross-serial dependencies, but there is an applied sentence that's implied by this sentence. So, if you just say the sentence, he didn't give the presents to Mary, but I think Bill did, what that actually means is that he didn't give the presents to Mary, but I think Bill did give the presents to Mary. And now you see the give has to align with this give over here, la has to align with this la over here, presents has to align with this presents over here, and so on and so forth, and you create an arbitrarily large number of these crossing dependencies. And that's exactly the type of thing which means the language is not context-free. So, if you count these types of examples, then we could say that English is not context-free, but it's currently, an ongoing debate as to whether, English just by itself is context-free or not. Okay, so what have we established in this presentation? We've seen that English is not a regular language. We know that for sure. So there's no finite state automaton that can capture all of the complexities of English. And we also know that it seems not context-free. So it looks like context-free grammars are probably not a very good way of modeling English. They get a lot of its features, but they don't get it entirely correct. So where do we go from here? Well, it turns out there's a whole hierarchy of different language classes we can consider. So in this presentation, we just considered regular and context-free languages. And so regular languages are basically the smallest class of languages. And then if you step one step out of there, you get the context-free languages, and that's a little bit more general. But you also have higher classes of languages, so bigger classes of languages, that include more languages. So you can have the context-sensitive languages, and then finally the type 0 languages. And so you might ask, why don't we start from considering the most general case, the type 0 languages? We know for sure that English is a type 0 language, so why don't we just start from there instead of starting from the regular and the context-free languages? And the answer to that is that if we start with the type 0 languages, it doesn't give us much information about the structure of English as a whole. So going back to the example of the decision problem, with the regular languages, you can solve the decision problem in O of n time. With the context-free languages, you can solve it in O of n cubed time. We know that for sure. Well, what happens when you walk into the realm of the context-sensitive languages? What happens is that you no longer get an upper bound on the time that will take to run at all. So with the context-sensitive languages, the best I can tell you is, well, the algorithm will stop eventually. We don't know when, but it's bound to stop eventually. And what happens when we go to the type 0 languages? It's even worse. All I can tell you then is, well, it might stop, it might not stop. The algorithm might just go on forever, never telling us an answer. And so you can see why we started the regular and the context-free languages is that it gives us a useful model to think about. Okay, so where is English? We think that it's definitely contained within this pink circle, the context-sensitive languages, but we've seen that it's probably outside of this yellow circle, the context-free languages. And so you might think, are there language classes that are in between those two? And it turns out there are. So these are called the mildly context-sensitive languages. They're in the in-between space between the context-free languages and the context-sensitive languages, and there are all sorts of models that we're considering in order to figure out what is the best way to model English once and for all. And there's no one right answer to this, but the better a model we can figure out, the more useful it'll be in the future when we're developing machines that can talk to humans. Alright, so thank you for listening. I really hope you enjoyed. I really hope you learned something about automata and grammars and things like that. And I have some, if you want to learn more about this topic, I have some stuff down in the description for you to check out if you want to learn more about the topic. So thank you so much for listening. Let me know in the comments if you enjoyed this video and you want me to do sort of more of this content in the future, because these types of videos take a long time to make, and I don't want to waste my time doing it if nobody wants it. But yeah, thank you so much, and I hope you learned something.